Alright, what's up guys? This is Probabiliy by Pitman, chapter 4 review section, problem number 13. Okay, cool. Local calls are coming into a telephone exchange according to a Poisson process. Okay, why am I highlighting it? That's weird. Okay, are coming, let's just highlight it, that's easier. Okay, local calls are coming into a telephone exchange according to a Poisson process with the rate, lambda local calls per minute. Independently of this, long-distance calls are coming in at a rate of lambda distance calls per minute. Write down expressions for probabilities of the following events. Okay, part A. Exactly 5 local calls and 3 long-distance calls come in a given minute. Okay, it seems simple enough. First, let's define our 2 random variables. We'll say lock, or local, is a Poisson process of lambda loc as specified above. And we'll do the same thing for long distance, where dis is Poisson process of lambda dis, where dis is distance. Okay, now that we have defined this, it becomes pretty easy, I think. So exactly 5 calls and 3 long distance calls come in a given minute. So note how they say lambda loc calls per minute and lambda distance calls per minute. So basically it's the rate per minute, right? So our problem's asking in a given minute, so that means we don't have to modify this rate whatsoever since it's already accounting for 1 minute. Just for bookworking, we'll just say that loc subscript 1 is Poisson process 1 times lambda loc. So basically if it was like given come in 2 minutes, then we do 2 times lambda loc because we want the number of arrivals in 2 minutes, if that makes sense. This is really just for bookkeeping. It'd be dumb if you had to do this otherwise, but I just want to make sure it makes 100% sense. Okay, so now that we created these new random variables for our part A situation, we'll just say probability that loc 1 is equal to 5, so 5 local calls, and dis 1 is equal to 3. So we should know that these 2 Poisson processes are independent of each other. So because they're independent, we can split the probability. So loc 1 is equal to 5, and that's a messy 5, whatever, you guys know what it is. Okay, probability distance 1 is equal to 3. And from there we can just do a simple Poisson. So e to the negative mu, our mu, alright, lambda. Actually, no, that's dumb. Okay. So the mu in our situation is just this stuff. So for local, it's lambda loc. So e to the negative lambda loc times lambda loc to the fifth, to the 5th power, all over 5 factorial times e to the negative lambda distance times lambda distance to the cubed, and then over 3 factorial, and there's our answer, ladies and gentlemen. Okay, part B. Exactly 50 calls, counting both local and long distance, come in a given 3-minute period. Okay, so basically in this problem, we don't really care if a call is local or long distance. So what we can do is create a Poisson process where we combine the 2 rates, or we combine the 2 situations, since we really don't care which is which. We're just looking for the total number of calls, regardless of whether it's local or long distance. So we can create a new Poisson process that just combines the 2 rates. So basically it totals the amount of each per minute. So we just get the total number of calls per minute, if that makes sense. So this new Poisson process would be lambda loc plus lambda distance calls per minute. However, we're not done just yet. Note how they're saying it's in a given 3-minute period. So we didn't really have to count for it in the previous problem. I wrote it out anyways, but we have to do lambda loc plus lambda distance. So again, that's because this is the rate of total calls per minute. but we want the total calls in 3 minutes, so we'll multiply this by 3 to account for that. And this is the one we'll be using. I'll just call it B. That's kind of messy. I'll call this random variable, Poisson process random variable that we're going to use called as B. So now that we know that, they're asking us the probability of exactly 50 calls in a 3-minute period. Okay, pretty simple. Just do the exact same thing as in part A. So e to the 3 oh, that has to be negative, don't forget that. Then lambda log plus lambda this to the 50th power all over just thought of something embarrassing I did. I was cringing at it, if you're wondering what that weird noise was. Okay, cool. Yeah, that's our answer for part B. Yeah, okay, cool. Part C. Starting from a fixed time, the first 10 calls to arrive are local. Okay, so this is slightly more complicated, but it's still not that complicated. Starting from a fixed time, the first 10 calls are local. I'm gonna pause real quick. Alright, sorry about that. I just wanted to make sure I was remembering correctly. So, remember how the problems asks, starting from a fixed time, the first 10 calls arrive are local. So that means we're working with n equals 10 total calls, and we want 10 of them to be local and 0 of them to be long distance. So we'll say good, which is local, is equal to 10. Bad, which is long distance, is equal to 0. Sorry, I had to go check out something. Okay, so we have 10 total trials or calls, of which 10 are local, rate, yeah, and then 0 are long distance. So this should remind you of some sort of distribution, because remember, each call is independent of each other. So it's like 10 independent Bernoulli trials, right? Where each trial is whether it is local. So if you haven't figured it out, this is just a binomial distribution. So we'll call our variable, I don't know, x, binomial with n equals 10, and then p equals, and then since good is a local call, we have to figure out the probability of a local call. So this is actually not as it's kind of confusing, I guess, but once you think about it, it's pretty intuitive. You can just make a proportion where it's like lambda local over lambda local plus lambda distance. Since there are two situations in our outcome space, you either get a local call or a long distance call. So an easy way to figure out the probability of a local call, since there are only two possible outcomes, is just get the rate of a local call over the rate of local call plus the rate of a distance. So like if you get 2 local calls per minute and you get 5 long distance calls per minute, then our proportion would be 2 over 2 plus 5, so 2 over 7. I hope that makes some sense, since you're just creating a proportion, right? It doesn't matter what constant our rate is multiplied by, because they made it a point to just say starting from a fixed time. They didn't give us like the actual time range. So using this, we can have like the actual proportion, and we don't really have to worry about time and stuff like that. So now that we've created a random variable, they're just saying p of x equals x, or sorry, x is equal to 10, and it's just a simple binomial random variable, 10, 10, power, and then so this would be lambda distance over lambda log plus lambda distance for the same logical reason. I'm just gonna write 1 minus lambda log plus lambda distance, but you should know that it's just the same thing with lambda distance at the top. the 0th power, and then since 10 factorial 10 is, or sorry, 10 times 10 is just equal to 1, this is equal to 1. So our answer is lambda log plus lambda dis to the 10th power, and that's our final answer. Thanks for watching, and I hope that helped at least somewhat.